I mean A epsilon. I should use a different symbol. Call it C epsilon. It's something totally different, so it's not confused with this stuff here. I've got an event, and I want the probability of that event to be 0. All right, so these questions are the same. That's how you apply this. All right? And so again, that's what people do to create the beautiful results like the Martingale convergence theorem that you then apply for your algorithm. So you probably will never ever use these arguments in your life. But this is how the beautiful results that you do apply are actually established. The Borel-Cantelli lemma is like an absolute workhorse in convergence of stochastic processes and all. Okay. All right. So cool. So it's really useful to go back to my example. So the coin flip is a perfect example. Everything works out wonderfully. But let's make it harder. Let's say the probability of the heads goes to 0. So it's a very unfair coin. You know, the probability of getting heads gets smaller and smaller as I flip and flip. But the coins are independent. I hate to use the word outcome because we've made a very precise definition of outcome as an omega and a big omega, but outcomes in the informal sense. I have an outcome, hey, I observed a heads or a tail. So I can apply B, and I can go through and I want to ask the question, will I get a heads infinitely often? I can apply this theorem because I've got independence. This is what I would call rho n before. So we know that the summation of rho n is equal to infinity. It's basically like the partial sums of 1 over n is approximated by a logarithm. You should all know that. The sum of 1 over n is infinity. And therefore, as we just proved, the probability of getting heads infinitely often is 1. Right. So that's all we need. So give me any dumb coin. All you have to do is check to see that's infinity. The probability of getting heads infinitely often is 1. For the fair coin, of course, you're summing a half infinitely often. That's pretty infinity. so of course you're going to get that. If it was 1 over n squared, nope. Then the probability of getting heads infinitely often would be 0 because we could apply the other result. All right, cool. Now, it's really useful to go back and look at something similar. All right. So go to our friend from last time where we're looking at the closed unit interval, all numbers between 0 and 1. We have what I call the Borel sigma algebra, the smallest sigma algebra containing the open sets, open intervals, and P is a uniform distribution. And let AN be equal to just to the interval, the closed interval from 0 to 1 over n. All right? So I'm going to test you. Do you understand the definitions? What is AN infinitely often? Forget the mathematical definition. What outcome happens infinitely often? Yeah, I heard it. Just just one little number. It's just 0. And which is equal to the intersection n equals 1 to infinity of the union k equals n to infinity of ak. All right. Because this union, these guys are decreasing. As you let n go bigger and bigger, they're decreasing. So taking a union doesn't change anything. That is just equal to an. And when you take the intersection of all these guys, you throw away everything except for 0. So we know the probability of this is 0. For the uniform distribution, the probability of a point is 0. But you see that the row ends are the same as we had in the other example. So you really have to be careful. If you don't have independence, you're dead. And this is the most grossly non-independent situation imaginable. I mean, here we have the probability of AN union AM is equal to just AN. Take the smaller one. Under what conditions we have, if n is the bigger, the union here, and so n is smaller. Right? I got that right? If m is bigger, I'll get a smaller set. So I take the union, I just pick the bigger set. All right? And the probability of the product is obviously not that. So that's a credible gap in independence. Oh, I'm sorry, that's a union. So that's, cut that. I flipped it around. I want the smaller one. And so the smaller one is n's bigger than m. I wanted intersections. Yeah. Go for it.
Isn't this just the difference between continuous and discrete?
No, not at all. Not at all. It's not the difference between continuous and discrete. Yeah, not at all. Because, I mean, in fact, I could map this to a continuous world. Like I was discussing last lecture, looking at sequence space and looking at an interval, it's almost the same thing because I can map between the two. No, it's really the fact that it's this gross lack of independence. That's what's doing it. Yeah.
Here was just the discrete points 0 and 1, the discrete outcomes.
Well, then I wouldn't have enough events. I'd be,
Okay.
I wouldn't even be able to talk about, yeah.
If you take a summation of the row ends, the summation will be infinity, right? So why is that the probability of A and I was 0?
No, well, the thing is, I mean, here I got 1. Because I was able to apply my theorem. I said that if the sum is infinity and the events are independent, I get this beautiful result.
You also have the first part which says that if the row n is finite, then we have, if the summation of row n is finite, then we have probability of A and IO is equal to 0. But we don't, that doesn't satisfy.
Well, we're not applying that now. I mean, right now I've set this up so the sum is infinity. Right? So this is just saying that here's an example where I'm getting the sum is infinity, yet the probability of AN occurring infinitely often is 0.
Basically,
so it's just
the converse is not true.
Yeah, well, it's just saying that independence is necessary. Yeah. You really need. If you don't have independence, you're dead. There are ways of weakening independence. Some sort of, lack vanishing memory. Sort of. There's generalizations, but we will not do that. All right, is that clear enough? And again, this is really the motivation, convergence of algorithms is really we don't really care about coin flips. So Yeah, I don't know if it's, I mean, it's not worthwhile going to another definition. So basically, this is one big workhorse in convergence theory. Another one is transform techniques. And so you take signals and systems, you're forced to learn about Fourier transforms, Laplace transforms, so forth. In stochastic processes, it's the moment generating function and all of that. And the value is exactly the same. Laplace transforms are beautiful objects. But in the stochastic world, they're way more beautiful. I mean, what you get out of transform techniques is much, much deeper and much more varied. I'll write it down again, and I think we'll just break then. So let's go through this list, and we'll develop it next week. What do I call it? Phi. I want to follow the notation of the book, yeah. So I've got a random variable x, and I take a sort of Fourier transform, in a way. Now you say I'm cheating, that's random, there's a j sitting there, and I've defined random expectations of real things. But we all know you can express a complex exponential in terms of sines and cosines, so you just define it in terms of the real and imaginary part. And this is bounded, x is real, so this is bounded, so the expectation is always well defined. So this is used in limit theory everywhere. You've heard of the central limit theorem. I know 50% of you say you have. You indicated that in that handout. To prove the central limit theorem, just apply this. Edgeworth expansions, all the variants of central limit theorem are based on playing around with this object. And again, this would be equal to an integral of e to the j u t f sub x of t dt if fx is a density. So that's not quite a Fourier transform. It's like an unnormalized inverse Fourier transform because they left out the minus sign. That's too bad. I wish there'd been more collaboration between physicists and probabilists. Everything gets flipped around. But you see that looks familiar, right? I mean, it's something you played with. And unfortunately, there's another thing. There's the moment generating function. Why do we have to come up with another name? The thing is that there's a whole world of application of the moment generating function, which is completely distinct from the world where this is applied. And so that's why this comes up. And so obviously, if you just stick in a j, you'll get this. So phi of u is nothing but lambda of ju. And again, this has another world. Of course, I mean, I'll review it next time. This language is because you can compute moments. Once you have this, that's not why we care about it. This is what leads to relative entropy, as I said. And that is what leads to bounds on channel coding theorems and all sorts of things. It's the center of the universe in information theory. And I really love explaining the geometry of that. This is beautiful geometry that comes out of this boring looking thing. It's absolutely amazing. So we'll do that over the next weeks. All right? But this is a good time to stop. All right? So until next time. And I'll hang, if there are any questions, I'll hang around. You had a question on the homework. I guess I've answered it. But I'll be around.
Thank you.